Okay, we're going to continue on our gas law worksheet here with the next section. You have completed your Boyle's Law certification, and we are now going to move on to doing the next section of problems called Dalton's Law of Partial Pressure. So you can see that if you just reference your question worksheet. And I'm going to help you out on this video by reading through the questions as we are talking about them. Okay, so just get through this. These you set these problems up nicely. You saw that there was some challenges going from kilopascals to pascals, and hopefully you learned on the fly with those problems, and I'm looking forward to seeing some nice assignments for that. Okay, so now we're moving to that next section in the book, and it's called Dalton's Law of Partial Pressure. So I'm going to go ahead and read question 7 here. It says, determine the partial pressure of oxygen collected over water if the temperature is 28 degrees Celsius and the total gas pressure is 98.74 kPa. So, like in this room right now, maybe let's say it was 100 kilopascals, average day. About 20% of that pressure is caused by oxygen molecules hitting me. So it's a partial pressure. But one of the key things to these problems in this application, which we are actually going to do in lab, is you will see that number 7 talks about collecting over water or water displacement. So as you're doing these problems, you can just put your answers right in the notes. I may ask you to submit some parts later, but you can just have good examples in your notes. So this sends up a little warning symbol to us, like we're like, hey, collect it over water, and you need to know what that is before we can move on. So the one thing that immediately it tells you is you're going to have to use your blue sheet. So if you want to get this at the ready right now, it's called the vapor pressure of water, and it's in your packet of colored sheets, kind of on the back of the one that you may or may not have used for your metric conversions. Okay, so we've got this blue sheet at the ready right now, so we will be needing that. But let's do a little diagram in our notes, a nice diagram of what it means to collect something over water. So like this would be fair game for a test or an assignment, where I'd say do a diagram of collecting hydrogen over water when you react magnesium with hydrochloric acid. So you're going to want to have this, and probably recommend maybe hitting the pause and getting some good detail to this drawing. So you can see what we have here is a flask that has a thistle tube. This is a glass tube which has kind of a funnel at the top. It's very important that this stays submerged under the liquid. So you can add a bunch of liquid to this. So what this allows you to do is maybe start by putting the magnesium chunks on the bottom. Now we know once the acid is added, it will begin reacting. And you don't want to lose any of those bubbles or that gas pressure, so that's why it's nice to just pour it, and as soon as a bubble comes out, it's got nowhere to go but up and out this. And where does this go? It goes into a big pan of water, And you got to make sure this whole thing is submerged underwater. And then when it bubbles up, guess what you got up here? Hydrogen gas. Okay? So that's a really good diagram of how we are going to collect gases over water. When we do the lab, those of you that will get a chance to do that, we're going to use a butane lighter. And we're going to figure out what the molar mass of butane is using the lab. But we're going to collect that butane underwater by just taking a big graduated cylinder, putting it underwater, and bubbling the gas up. And in our case, this would be methane gas. Okay, so here's the one tiny little problem with collecting a gas over water. As this hydrogen bubbles up, works out great. This is mostly hydrogen, but there is an impurity in there that's inevitable, that we're going to have to look at and we're going to have to fix. So there's another gas that got in here. And it's not any gas that was dissolved in the water, like oxygen or anything like that. So by process of elimination, if you're like, the only other possibility for a gas, since this is hydrogen and it's bubbling up through water, by process of elimination, your only other possibility is that is water vapor, water in its gaseous form. So water vapor is always going to be a part of that. So that's the bad news. If you collect something, you're always going to have an error because there's going to be little water molecules in there taking up space just like the hydrogen gas is. Now the good news is you can use your blue sheet to correct for that. If you know the temperature, you can go to your blue sheet in your packet here, all right, and you can look up what the pressure is in millimeters of mercury and kilopascals of water at varying temperatures. Now here's what's kind of interesting. If you look at that blue sheet, and if you look at a temperature of 100 degrees, then the partial pressure of water vapor then becomes 760 millimeters of mercury, or 101.3 kilopascals, which is 1 atmosphere, which means at 100 degrees it's going to start boiling. Okay? So that's a little fun fact there for you. All right? But we've got them for all the temperatures. The colder it gets, the less water vapor there is. That should make sense to you. They kind of get more energy and break free. So I can utilize this to solve that problem. So let's go ahead and take a look. But before we actually do the problem, I just want to show you this little video of when we did the lab a few years ago at the end. So
you just bring her right up at the base of that.
So this is kind of...
Okay, and then she gets a nice fire there. Okay? Ready?
So what we have is
so you work it over in the corner.
Wait till it's lit.
Don't go yet.
This is butane inside of here that we trapped, collecting it over water. There's your big bin of water. And what we're going to do now, we're going to light the butane on fire, which is optional.
That'll burn for a little while. See the butane's coming out of there? Now put it upright. You can kind of see.
The Olympic torch.
Ladies and gentlemen, thanks for coming.
Okay, so you can kind of get the idea there that, whoops, I'm going to hit pause for. Sorry about that. We were going to end up watching a bunch of YouTube videos there. That kind of gives you a little thing, hopefully get fired up about coming and doing that lab. But we'll get a chance to actually do this, where you bubble a gas over water and then light it on fire at the end if you want, in a safe way, of course. What we're going to do is going to go ahead and apply these things for question number 7. And if you don't have a copy of this, that's okay. Make one if you can. But you might want to, in your notes, write down kind of, what the information that was given to you in here, so that if you know, you won't have quick and easy reference to it. Of course, this is posted as well, so we'll post that just about every day. So here's how we do this problem. We say that P TOT equals P sub O2 plus P sub H2O. So these are all partial pressures on the right side. So you can guess the P TOT is the total pressure. Now, when you're doing these problems, you need to follow this format. You're going to put a capital P, lower TOT, and then you put the formula of the gas, if it is known. You put that formula in there. All right? So this pressure of O2, partial pressure of H2O. All right, so the total pressure is given, and you can just look that up in the problem. That's going to be 98.74. It says determine the partial pressure of oxygen, so that's my unknown. But how do I get this partial pressure of water? Well, it says we're at 28 degrees, so get your blue sheet out, and since the first pressure's in kilopascals, we'll get the blue sheet and we'll go 28 degrees and find out what the pressure is at 28 degrees in kilopascals, and hopefully you can see that is 3.78. So now it just comes plugging those numbers in. Okay, so again, this was given to us in the problem. This is our unknown. This you look up on the blue sheet. At 28 degrees, water will exert a pressure of 3.78 kilopascals. Now, that's not very much pressure. If you think about it, in kilopascals, the whole room has a pressure of like 101, right? So it's small, but you can't make the assumption that that oxygen that's trapped in there has the same pressure as the environment. It's always going to be a little bit less. As you can see here, we're just going to subtract, and in terms of sig figs, when you're subtracting, it's about place value, right? It's our scales that we used in the lab. 2 places to the right, 2 places to the right. So my final answer for partial pressure will have 2 places to the right. When you take 98.74 minus 3.78, you can see I just kind of fixed that pressure a little bit. It didn't exactly equal the pressure of the air. You had to get that water out of there and say, well, we know it's 3.78, so I can just subtract that out, and this, the partial pressure of oxygen, is 94.96 kPa. Okay, so we'll continue to do these problems together, and then I'm going to let you try some on your own, giving you the answers. So if you go to now a Dalton's Law video 2, that will, or the second video for Dalton's Law. You will open that one up, and we'll do problem 8 and 9, and then you can work on 10.